So, we would do today graph mean cut, and in that kind of see applications of this. Now, the algorithm that we would talk of for graph mean cut, I define this problem for you shortly, but this was like a very, this is a very, what should I say, very important as well as a classical problem in graph algorithms. And there were algorithms, the one I would discuss today was by someone called Kargar, coming up in the 90s, 1990s, and you would understand that it's like it's a such an elegant and beautiful algorithm that for it to have come so late in the day in computer science should have come much earlier. Now, so Venkatesh, I think, had done some randomized algorithms for you, but they were on numbers, arrays. This is kind of your first foray into something which is like kind of just beyond numbers. You would get into graphs. So, I assume that everyone knows what's a graph, right? You have a set of vertices and a set of edges which is nothing but a subset of V cross V. So, it is a relation, right? Okay. The graphs can be directed graphs, undirected graphs, connected graphs, simple graphs. So, in here we would be considering simple, undirected and connected graph, right? The simplest version of a graph that you can think of. So, what is a simple graph? That for any two vertices you allow only one edge. So, you do not allow multiple edges, as well as you do not allow any self loops, because I said edge is a subset of V cross V, right. So, this XX can also be an edge, it is kind of a self loop on a vertex. So, I disallow self loops, I disallow parallel edges as well. Fine. So, what is a minimum cut for G? What you want to do is as follows, and this is a problem useful in clustering, in partitioning, in many places. I mean, the reason it is very useful is like many real life applications you can abstract as graphs, and then you want to divide it by tearing off the minimum number of edges. Okay. So, here is the definition for minimum cut. What I want to do is, I want to pluck out some edges from the graph such that the set of vertex V breaks up into two disjoint components V1 and V2. Is the minimum number of edges So, mind you, this is a partition. So, partition means there is, if you look at V breaking up into V1 and V2, then V1 intersection V2 is a null set. So, I require the vertex set V to be broken into at least 2, right. So, think of this as 2 vertex sets. So, minimum number of edges I need to pick out from the graph such that the graph breaks into 2 parts. So, is the problem clear? Fine. So, let us look at an example. So, here is a 5 vertex graph. So, what is its mean cut? 2. Which way would you cut? So, you would cut possibly the edge, right. So, this is your mean cut. So, 5 on one side, and by removal of the edges 3, 5 and 4, 5, the vertices 1, 2, 3, 4 on the other side. So, this is a cut. Fine. Now, for a general graph G, what would you do to find the minimum cut? How do you proceed? What is your number of possibilities? Huh? Hold on. Do you call that an algorithm, right? An algorithm is like exponential. There are exponential algorithms for some certain problems, but for a problem as simple as this, would you want to spend exponential amount of time? Right? What you said was, I can have at most NC 2 edges in this graph. It is a simple graph, and so I either keep or delete each edge, 2 possibilities. So, you are looking at 2 to the power of n choose 2 possibilities. Yeah.
N minus 1 edges, because at most one element can be connected to n minus 1 and one vertex would be connected to n minus 1 vertex. But edges.
Yeah. So what I mean, what is your? I mean, I want an algorithm.
At max, it can be connected to only n minus 1 other edges.
Mm-hmm. So
For a perfect figure, perfect graph, n minus 1 would be the answer.
no. Look into this. Hold on, come. So, I have a graph, right? Not all graphs are completely connected, right? So, I want a set of edges whose removal makes the graph into 2 parts. So, how come I have a predetermined answer like n minus 1? There can be graphs for which only one edge is the answer, right? So, give me and try to think of an algorithm of a sequence of steps which would lead you to find the minimum cut. Hold on, yeah. start with the smallest degree vertex, okay. That's a good idea. Oh, right, this example is actually that. You did the smallest vertex, right? Smallest degree vertex. Let's see. Think of this graph, which is kind of a so I am looking at a particular kind of graph which is as follows. So that means for any two vertices, so I sort of, so the graph looks like this. So it's n by 2 vertices on one side, n by 2 vertices on the other side. This n by 2 connected fully among themselves, right? And this n by 2 fully connected among themselves. And for two designated vertices, there is an edge. So this is now a complete, simple connected graph on n vertices. Agreed? What is the size of the minimum cut? But if I go by minimum degree, which vertex would I pick? Somewhere inside it, right? So minimum degree is like kind of tempts you to get into minimum degree, but it's not going to give you the answer. Yeah, some more ideas. So minimum degree is like, but I would appreciate your idea in the sense that minimum cut should have something to do with the degree value. Think of this. Say for example, minimum cut is of size k, right? Then if you had in this graph a vertex whose degree is less than k, then you cannot have, right? Because if you did have, then you would have taken that vertex on one side of the partition, the rest on the other, and the number of edges from this vertex to that side is less than k. Cannot be, right? Because your minimum cut is of size k. So minimum cut has something to do with degree. We will explore that. But again, let us have some more ideas before that. Yeah, so this minimum degree idea is not going to work algorithmically. It might help me in proving certain bounds, but that we will see later on. So, a takeaway from your suggestion is that the degree of each vertex in this graph should be greater than equal to k, where k is the size of the minimum cut, right. So, this is a takeaway. Fine. So, let us do this. Maybe we can take this as a lemma. This is our takeaway. For all vertices in this graph, degree V is greater than k, where k is the size of the minimum cut. So, proof I have already given, you do it as an exercise. So, you just argue that if it is otherwise, then the minimum cut has to be greater than k. So come up with ideas for the algorithm. We had one characterization. You know by now randomization. Can you get me some ideas from there?
We can pick any edge randomly and then check if a path exists between any two vertices of the remaining graph.
Okay, then so her idea is as follows. I have this graph, and for this graph there exists, mind you, there is no guarantee that your minimum cut set, the set of edges, would be unique, right? There can be many such minimum cuts in the graph. How many we will see later. Now say for example, you have this number of edges is E, of them you know K is the minimum cut size, right? So say there exists a cut C. Before I get into it, randomized algorithms are of two types. One is known as this Las Vegas randomized algorithms, the other is Monte Carlo. So the ones Venkatesh discussed in the last day where there is no error are known as Las Vegas, and the one where there might be errors, where obviously I would put a probability bound on the error, would be this Monte Carlo algorithms. So now what I am going to do is I am going to learn the first kind of Monte Carlo algorithm. So I am allowed to err, right? I am allowed to make errors, but again we would prove a bound on the probability of that error. Fine, okay. So the algorithm is as simple as this. What you do is pick an edge at random, uniformly at random, pick an edge. Then what you do is so this is an edge with between two vertices. You have picked uniformly at random from the graph. Collapse these two vertices into a super node kind of thing. So you started with an n vertex graph. You picked an edge uniformly at random. Collapse these two vertices at the end of this edge into one vertex, right? Now this new graph has n minus 1 vertices. You need to form these edges in this new graph in the following way. This edge which was between these two vertices gets deleted from this graph, right? What I have to now do is, what about edges that were going out from these two vertices? What I do is, in the new graph, all other vertices remain except these two. These two vertices has been replaced by a kind of a super node. From this super node, I put edges to those vertices to which it earlier two vertices had edges to. Done? I again repeat the process in the new graph. Again pick two vertices. Now of the two vertices of an edge picked uniformly at random from this new graph, maybe one vertex is a super node, right? But again you do the same thing. Collapse, we'll see. collapse, again reassign edges, keep doing. So, at each stage you are reducing vertices by 1. Stop at the moment you have only 2 supernodes, right. You started from n, stopped when you had 2 supernodes. So, how many iterations did we do? N minus 2. Started from n vertices, stopped when we had 2 supernodes, n minus 2 iterations. Done. Now, what I do is, now see, corresponding to these two supernodes, there are vertices inside this, vertices inside this. That I declare as my partition. All edges going across are the cut. Is the algorithm clear? Okay. Let us do a small example with this, for this algorithm. With that, I would do 2, 1. It's like, you understand why I do 2. So, contract the edge 3, 4. So, if you contract the edge 3, 4, you have a super node corresponding to 3, 4. You have 1, 2 as earlier. This edge is undisturbed. Now, from 3 there was an edge to 1. So, from this super node there should be an edge. There was also an edge from 4 to 1. Right, I said when you collapse, whatever edges that are going out from these two ends should be retained. So, 3 had edge to 1, I keep it from 3, 4 from this super node. 4 had an edge to 1, I also keep that edge. No longer this edge is a simple graph, this gets to a multigraph, because I start having parallel edges. Similarly, you have these two edges. Done. So, I have got rid of one vertex. Now, I have come down to 4 vertices, of which one is a supernode. Next, what you do is contract 1 and 3, 4. What do you get is a supernode of 1, 3, 4, and you have 2 and 5. then contract two and 1, 3, 4. Yeah.
Based on the number of,
What? I didn't get.
so here, do we contract based on the number of edges between the,
No, as I said, pick an edge uniformly at random.
so that if we take 1, 3, 4 and 5,
Hmm.
like if we pick 1, 2, then
No, there can be many choices, as I said. I'm just looking at one particular choice.
yes, so if we randomly pick and club them, so at the end, whatever we get the degree sequence will,
What degree sequence? There's,
no,
let's just go with this example. Let's just go with this example. You will start appreciating things. Yeah.
Is it compulsory to take the?
There is nothing compulsory. I said
We can take any.
there are a bunch of edges in there. No edge is lost. You at any point of time pick an edge uniformly at random. Right?
sir, when the contracting 1 and the supernode 3, 4, will we get a subgroup over 1, 3, 4?
Whatever it is. I have given you the rule. So I said I would stop when I have two supernodes. So I stop here. And I declare this as my cut. Right? Mind you, for each edge selected uniformly at random, when I collapsed, that edge is lost. Right? So just if you count the number of edges, you would understand which edges are lost. But what I needed was the partition of the graph into two subsets of vertices, disjoint subset. Now if you go back, this was what it was. Fine. Now what you do is, okay, so what was my algorithm? I picked edges uniformly at random. So for example, in this case, this was picked first, then so I contracted 3, 4, then 1, 3, 4 was like, this was picked uniformly at random, you got this one, and then 2, 1, 3, 4, this was picked uniformly at random, right? So when you collapse, as I said, all edges between these two vertices go away. Now that means if during this sequence of collapsing edges I never touch an edge that belongs to the minimum cut set, then I am done. But while doing this collapsing, if I ever touch one of those edges in the min cut, then I will make errors. Now what you do is, to get yourself convinced, you look at this sequence of contractions. So in here, what you do is, first you contract 3, 4, then you contract 3, 4, 5, next you contract 2, 3, 4, 5. Do this yourself quickly. On the same graph. So start with this one, first 3, 4. So you land up here, right? So you land up there. Then instead of contracting 1, 3, 4, you contract 3, 4, 5. You contract 3, 4, 5. And then see what you get. You will get something like this if you are correct. Now see, what you did was, the moment you contracted this 3, 4, 5, you had touched one of those edges. And that is why this is a unsuccessful case. So by now you understand that there are sequence of contractions which might lead you to the minimum cut, and there are sequence of contractions which might take you away from the minimum cut. Done? So let us sum up this observation that we had. So if you have not touched any one of these min cut edges in any one of these n minus 2 iterations, you are done. Agreed? Okay. But this is now a probabilistic event, right? You may touch with certain probability, you may not touch with certain probability, because you are picking up edges uniformly at random. So somewhere down the line I need to figure out that what is the probability that, now think of modeling this as a random process. I picked up in my first iteration, I picked up an edge uniformly at random. I was happy if this edge did not belong to the min cut. So, I need this probability. Probability that an edge picked uniformly at random in the first pass did not belong to the min cut, right. Come to the second iteration. In the second iteration, I will be happy if I had not disturbed a min cut edge in the first iteration and not even in the second. So, this is a conditional probability. So, in the second pass, I need something like probability that no edge of the min cut was disturbed in the second pass, given that no edge was disturbed in the first pass. Come to the third iteration. No edge of the min cut disturbed here, conditioned on the fact that no edge was disturbed in the first and the second. So, intersection of that. Are you now getting something like this? So, I would now define my event as, say, an event EI as an event that no min cut edge was contracted in the iteration I. I runs from 1 to n minus 2. So, if I can now figure out these individual conditional probabilities, then I am done with the error, right. Okay. So, this is the, now we will get into the formalisms. Any queries till now? No queries for me is always a dreaded, a very dreaded thing, huh? Okay. Let me now define my events before I make the effort to find them out. This n computing 3-way intersection is difficult. So, it is like computing n minus 2-way intersection would be more difficult, and so that is why people take recourse to this chain rule. So, now I know that this is equals to done. This is what I have to now figure out. So, finding this out exactly might be difficult. So, what I would be possibly happy with is a bound on this, that this is greater than equal to something, and its complement event is the other side, that you fail with a probability at most this. So, this is kind of the success probability. So, success probability I want it to be above certain thing. I want to give you a guarantee that it is always going to be something above something. For the failure probability, I would give you an upper bound on the failure probability. So here I would want kind of a lower bound. So that means I would want for each one of them a lower bound. Then I can kind of multiply them to get the final lower bound. So let us now try to figure out this lower bounds. If we can, we are done. Okay. In here, this will help us a lot. Now think of the first probability, think of the probability of E1. That is a very easy probability to figure out. Why? Because still the graph is kind of pure, no collapsing, nothing. So if you now look into this probability as kind of a fraction, in the denominator you would have the total number of edges, and in the numerator you would have k, right, the number of edges in the cut. So in the below thing, in the denominator, how can I now have, and mind you, this I want a lower bound on P E1. So that means I would want a lower bound on the number of edges. Now if you look into this result, so look into this result, this is true for all vertices. So take a sum over all vertices on both sides of this inequality. So summation of degree is what? Summation of degree is related to the number of edges, right? So when you sum the degrees, what do you see? Each edge contributes to 2 degree sum, right? So if you sum this degree, it should be twice of the number of edges on the left side. On the right side you get n into k, you are summing over all vertices. So you straight away get twice of E is greater than equal to n of k. So n, the number of edges is bounded by nk by 2. So when I write mod C, it means the number of edges in the cut. So an implication of The above lemma is the following. Because this is k and this is greater than equals to kn by 2. So, this is your nothing but so probability of this is no, that should be 1 minus 2 by n, sorry, that epsilon 1 was not contracted, remember that, I am sorry. Yeah, we will plug it later on. So, an edge of the cut is contracted in the very first instance is now you see a very low probability, right? It is a very low probability event. As I go along, what will happen is the number of edges keep reducing, these probabilities keep increasing, but again there I would show that they are not going to increase by too much. So, as this is less than equals to 2 by n, mind you there I need, here the inequality is on this side, there I need on the other side, and mind you I had defined is not contracted. So, these things would be probability of this E1 would be greater than equals to 1 minus 2 by n, right? Do you agree to this? If you have any difficulty in understanding, just pause here a little bit and get it clear. What was this probability? An edge in the cut is contracted at the first instance, right, when I started. Right. So, this is upper bounded by 2 by n. What is my E1? Event that an edge of the cut is not contracted in iteration 1. The complement was upper bounded by 2 by n. So, this should be lower bounded by 1 minus 2 by n, that is what I meant to say. So, this is like 1 minus 2 by n. Next I need to figure out this one, but to figure out this one the graph has now changed, because after the first iteration no longer the graph is looking as nice as this, but it is something like this. Agreed? Okay. Now think of this. I had this big graph G which I am contracting, and I am at some iteration J. So look at this new graph at this iteration, right. So you have done contractions, reached to a stage. Let us call this graph G dashed. Now if I get a cut in this graph G dashed, and with this, so if I get a cut in G dash, this is a partition, right. If I go back to the original graph, a cut in G dashed is also a cut in G. But not the other way around. As a proof of what I said, mind you, I took a minimum cut here, went back there. So cut in here was preserved as a cut in there. Right? But there is no guarantee that a cut in there will be a cut in there. By cut I mean minimum cuts. Right? I will crucially use this observation that a cut in this contracted graph is also a cut in the original graph. So you have gotten to this graph G dashed after j iterations. How many nodes are in this graph? After the first iteration it was n minus 1. So after j iterations it should be fine. Okay. Mind you, my goal is now to find these conditional probabilities. So I am looking at a situation where after the jth iteration no edge of the cut has been touched or contracted. So I am in this situation to set up the conditional probability. J iterations gone by, I know now number of supernodes is n minus j and none of my cut edges has been touched till now. Keep a note, not the other way around. So every cut of G is a cut of G. Every cut of G dash is a cut of G. If that be the case, then this should still hold. That if you now look into all vertices of G dash, where there are now n minus j supernodes, all of their degrees should be greater than equal to k. Otherwise, if it was less than k, then the minimum cut size of the original graph G would not have been k, it should have been something less. Agreed? Right. So because of this implication, because of this, it implies that So, number of edges in G dash is at least what? Earlier what it was? K into n. Why? Because you are summing over all vertices. In this new graph, how many vertices are there? N minus j. Right? After j iterations, there are n minus j nodes remaining. So now this set V has gone to some V dashed, but the cardinality of that set V dashed is n minus j. Right? So on one side you would sum up to n minus j. Right? So it would be k into n minus j by 2. So do it as a formal exercise. So let us call this set to be E dashed. Right. So I am not writing the big thing. So what should be in here? That probability that a cartage was not touched at the jth iteration, given that the cut is still there. There was no disturbance till now. So in effect what I have done is I have got, again you see, so this was an upper bound 2 by n. For the jth iteration I have got an upper bound of 2 by n minus j. So now if you go back and plug there, for the jth step it would be 1 minus 2 by n minus j, right. Now what I suggest is, now you have got all terms, right. Just do this product and see for yourself what is coming. Now I have everything ready, all probabilities ready. This I had figured out, and each one of these intermediate steps I have figured out. Now just go through the motions, go through the calculations. I suggest you write a few terms before this last term and do this simplification. Professor, I have 10 minutes more, right? Yeah, okay. What is this coming out to? This should come out to a nice expression. See, you'd get a n minus 2 in the numerator here, and you'd get an n minus 2 in the denominator here. So that should cancel out. So similarly, something here should cancel out with another term there. So there would be such nice cancellations. And you'd be left with this. If you do this correctly, it should come to this. Yeah, and there should be a 2. So that is 1 by n choose 2. Okay. So this was the probability of success. But what I am interested, I told you is I would bound the error probability. So it is the complement event. So final result what I have got till now is so that means this, right? So I promised you that I will give you a bound on the error probability. What is the error? That my algorithm could not find the minimum cut. But you should at this point of time tell me what the hell you are doing. You know, if n is large, you are saying that with almost probability 1, you have failed, right? Because as n grows large, 1 by n choose 2 goes down, and then you are saying that, well, with a probability of at most 1, anyway you will get a probability of at most 1, with the probability of at most 1, you have failed. So what the hell have you done? Now herein comes a trick of randomized algorithm for algorithms that has a one-sided error. Mind you, for a minimum cut, you could not find a cut that is less than the minimum cut, right? So if you had erred, the cut size would obviously be greater than the min cut. You agree to this? So this algorithm has one-sided error. If this algorithm has one-sided error, we can do something now better. What I would now do is, I will make, so this was my, so now think of the algorithm that I have designed for you as one black box, right? What I would do is, I would run multiple instantiations of the same algorithm, right, but independent to one another. So that means for your first box, for your first run, there was a sequence of contractions which was a random choice. In your second run, you will again make random choices. These two sequences should not be the same with high probability. You keep doing this, right, and take the minimum out of them. Now mind you, now your error probability was for one run it was 1 minus 1 by n choose 2. If you run it second time, your error would come to, it would now be a product, because these are now independent events, right. So 1 minus 1 by n choose 2 into 2, but if you are now going to run it multiple number of times, say n choose times, what is 1 minus 1 by x whole to the power of x? That gets you close to e to the power of minus 1, right. So what I do is, I now run it for n choose 2 times. My error probability would come down to e to the power of minus 1. If you run it more, you can even bring down the error probability. So for algorithms that has a one-sided error, you can do this. This is known as boosting the, well, you might say the error or the success. So if I say boosting the error probability, it means pushing the error probability down, and if I say the boosting the success probability means, right. So in here boosting the error probability meant that I wanted to keep it down. So what I did was I looked at the quantity and you can figure out so this tells us that I mean, I should be a bit. So what was the idea? This was one instance which had an error probability of 1 minus 1 by n choose 2. What I did was I kept running it multiple times. How many? N choose 2 times. Now obviously this comes with a cost. Your time complexity has gone up, right? So what time did one run of your algorithm take? Kind of what you did was figured out pick an edge uniformly at random, collapsed all edges that were incident to it. So for one, if you look at one contraction, you might take at most linear time, right? Because if you are contracting an edge whose one of the end vertices has a high degree, so has almost edges to everything, then you might end up taking linear for one contraction. You are doing n minus 2 contractions. So each run might take order n square, right? And n choose 2 is roughly order n square, right? Because it is n into n minus 1, the dominant term is n square. Now you have to choose what makes you happy. You give less time, your error probability is high. You give more time, you can bring down your error probability. Now that is your choice as a designer, what you would do. So you can do this exercise, that what if, say, instead of running n choose 2 times, say I run n choose 2 log n times and see what happens to the error probability. So the more number of instances you would run, your error probability would keep coming down. Mind you, it is because your algorithm has a one-sided error. If it was having results on both sides, this would not have worked. Now mind you, when you studied the algorithms which Venkatesh taught you, which were kind of those Las Vegas algorithms, your time was a random variable, right? And he showed expectation on the time taken for quick sort, for quick select, so on and so forth. Here the algorithm time has no randomization component to it, because I do n minus 2 iterations and I then contract whatever I like. So the time analysis, the time complexity analysis is a deterministic analysis, but the error thing is a probabilistic. So the algorithm is probabilistic, but the time complexity is not going to be a random variable here. Fine. So this is a Monte Carlo algorithm. As I said, you are allowed to make errors, but you want to put a probabilistic bound on the error.